Okay, I'm really sorry, a little slow getting started here. So I'm trying a couple of new things this quarter, so hopefully you won't feel too much like guinea pigs. So I'm going to do my best to publish all of these lectures on iTunes U, so you'll be able to download them. And at the very least, that should come with sound and the actual PowerPoint slides. And if we can make this work, we'll actually have videos of the lectures, which would probably be better because you can see how people are interacting, etc. So hopefully everyone's in the right room. This is Cosmology 20B, so Physics 20B. If you're in a wrong class, I won't be offended if you leave. Even if you're in the right class, I won't be offended if you leave. So just before I get in, the first thing I want to talk about is sort of administrative stuff and how we're going to grade, because I know people want to know about that. But let me talk a little bit about the content of the course first. So this course is Cosmology. Does anyone know what Cosmology is? You, sir.
Study of the universe.
Sort of, yeah. Yeah, the study of the universe. So cosmology is basically everything. So cosmology is the study of the large-scale universe as a whole, how it evolves, how it started, and where it's going. And cosmology is a really old subject. The idea of cosmology and origins was certainly around in humankind before there was science. But what I'm going to talk about is scientific cosmology, so it's attempting to apply the methods of science to answer some of the fundamental questions that people have often asked themselves, probably even before there was technically science. So for example, how old is the universe? How did we get here? How did the universe as we see it get here? How far away are the stars? When you look up at the night sky, how far away are those things? What are those things that are shining up there? How big is the universe? And then of course there's sort of, because it's cosmology, it encompasses a lot of questions that are more detailed questions, like you've heard about black holes. What are black holes? What is the Big Bang? What's dark matter? Those kinds of things. So it's those kind of questions, and what I think of as kind of fun questions is what we're going to try to talk about in this course. The textbook for this course is optional, but you're welcome to use it. It's 21st Century Astronomy by Hester and a few other authors. I think it's a good textbook. It's kind of light on cosmology, and I tend to really base everything I do and even test on my lectures anyway. So I say it's optional because you probably want to, a lot of people want to read a more sort of fluid account of a subject that I'm going to just present in a lecture, and so you're welcome to use that book there, and I'll provide reading suggestions for the lectures for you as well, if you want to do that. So how am I going to grade this course? So we have basically two midterms. And the first one is 25% of your grade, and the second one, which actually comes at the end of the course, is 35% of your grade. The second one will be cumulative, but it will emphasize stuff since the first midterm. So it will be sort of with an emphasis on later material, but I will ask you questions from the entire course as well. So it's sort of like a final. It's sort of like a final in the sense that I'm not going to give you a final exam. I'll give you a final paper instead. So here are the dates. Friday, February 8th is the first one. That's in your discussion section. That Friday, February 8th is the one discussion section that you have to go to. Okay? If you can't be in that discussion section, you need to contact me like now. Because there's limited space in those sections, and you can't just randomly go to any section to take your test. So let me know as soon as possible if you can't make this date. Okay, don't tell me the day before or something like that. The second exam is on the last day of class, March 14th. And that'll be given in this room. So the point of these exams, of course, so I really want you to learn about cosmology and like science and get something out of this course. That's my goal. And so the reason why we test is to sort of encourage you to do that. And so that's the point of these tests, is to make sure you're following along and paying attention. That's why I will even test you a little bit on even things like vocabulary, which I don't really think are that important fundamentally, but it's just a way of testing that you're paying attention and rewarding those who come to lecture or watch the lectures. There will be some mathematics in this course, but I won't overemphasize it. But because this is a general education science course, I'm required to have some math problems in this class. And of course, in order to really understand cosmology, you're going to need to do a little bit of math anyway. So that's kind of par for the course. But I'm not going to go overboard on it. I'm much more about concepts in this course. There's going to be 2 major homework assignments that I will assign here. Okay, and that'll be 20% of your grade. And then there will be a final paper, which is also 20% of your grade. And the goal of this is to help you explore the subjects we talk about in a bit more detail, to think more deeply about the things we're talking about. And the final paper is a little bit more freedom, but what I want you to do there is pick a popular cosmology article that's in the press. And I'll help you, I'll give you links to stuff like that as we go along. Pick something you're interested in and write a short paper on that subject, summarizing what it's about, talking about what you think of it, why it's interesting, how they actually did the observation to discover what they did. And again, we'll talk more about those things as the course goes along. Now, this course I try to make it so that you can access the relevant material online. So there's a course website that's already up. I will post PDF files of all the lectures there. I have a class blog, which I'm toying around with. So there I'll also post the lectures. I'll post podcasts of the lectures, and then additional material that I think is interesting, like little video clips and things like that, that are kind of good and interesting and associated with cosmology. And I'll send an email to all of you with these relevant links. And like I said before, I'm going to put all this stuff up on iTunes U as well, so you can have them on your phone. You can have these lectures on your phones and things too. So if you want to listen to them as you're walking across class, I'm sure you'll do that. Or you'll go to the gym and get really fired up that way. So this course, so that ends the introduction. Does anyone have any questions about that logistical kind of stuff? It's pretty straightforward. So check the schedule out online. So it'll talk about what we're doing in discussion sections, etc. Discussion section is canceled this Friday. And I will hand out the first homework next week. Okay. So this lecture, these are the subjects that it's going to cover. What is cosmology? The concept of looking back in time in cosmology, and astronomy in general, and talking about the finite speed of light and how that matters. And I'll end up this lecture with a discussion of the size of the universe, or trying to get a sense of scale in the universe. So let's see. Let's do this. Is that too dark? You sure? Okay. So I really like this picture. So this is a picture that was taken of the sky at night underneath this ancient Mayan temple. Okay. And what you see rising up above the temple there is the constellation Orion. And of course, we understand today that Orion is made up of stars, and those stars are very far away. And in fact, if you've taken an astronomy course, you might even know that this bright yellow star right over there is called Betelgeuse, and it's something called a red giant. It's a gigantic star, much, much larger than the sun. And in fact, Betelgeuse, at some point, maybe not too long from now, give or take 1,000 years, will explode as a supernova. And for a brief period of time is probably going to be brighter than the moon. But of course, the ancient people who looked up to see a view that was very, very similar to the kind of sky we see, they of course didn't know that. And the question arises, how am I able to tell you something like what I just told you? How do we know what's going on? right? I mean, of course, to them, when I say Orion is rising up, it's not really rising up, right? The Earth is turning to reveal it. But that's not the way they saw it. And in fact, that's not the way we even talk about it now, even though we know better. Okay, the sun does not rise, really, right? The Earth turns to reveal it. But how do we know? If you go back even farther now, what this is a picture of dawn as viewed from Central Africa. Now, of course, this is a modern picture because it was taken with a camera. But if you imagine yourself as one of the first humans to walk the Earth, okay, and you're living out on this desert, or it probably wasn't a desert, but you know, you're living out this area, you would see a sky that was not very much different than this. Now, the one thing that would be different is this thing over here is a distant town, so let's cover that up. But this is what you see. And you can imagine, you know, your ancestors looking up at this sky and asking themselves, well, what's up with this? What is this? This seems important. I mean, it's kind of awe-inspiring, but what is it? Now, your eye is drawn to the bright things. Obviously, there's the sun. But then there are these things, Venus and Jupiter, and even the bright stars. These things must be important. In fact, they behave in regular ways. Now, people also notice things like, well, when there are certain configurations of stars and planets in the sky, then things start happening like it starts getting warmer and it's a good time to plant food. Or maybe there'll be a migration of animals that we like to hunt. And so people began to think that, oh, there's a correlation between what's going on up in the sky and what's happening down here. And so it's not a crazy thing that people began to believe that those motions of objects up there in the heavens were perhaps controlling events here on the ground. Now, we now know enough about what's going on up there that this is crazy. The correlation doesn't really always imply causation. But they didn't know that, and that was a reasonable thing for them to think. And in fact, that's why people started studying the sky so carefully initially, at least we believe, because they thought it could give them additional power, additional information to predict what was going to happen. But fortunately, that deep peering into the sky is arguably what led to the scientific revolution itself. So let's flash forward some time. Let's say we had Aristotle looking at this same sky. How would Aristotle have interpreted this? Well, Aristotle would say, look, the Earth obviously is fixed. The Earth is not moving. And what's happening is these objects are rising up in the sky. And what's happening is Jupiter and Venus and the Sun are all orbiting around the Earth. And we're fixed. The interesting thing is, there's this band over here that maybe you didn't even notice. This is the Milky Way. Okay, this band of stuff. Aristotle really didn't know what to make of the Milky Way. In the end, he convinced himself that it was some kind of atmospheric thing. It was like the sky that was just messed up for one reason or another there. But it was pretty close to the Earth's atmosphere, and it was definitely closer to us than the stars and the planets. The interesting thing is, the Milky Way is the real clue here for what's really going on, because that's our galaxy. We live in a galaxy. And every single star you can see by eye is embedded in that galaxy. If we flash forward now to a new interpretation of what this would be, this is Isaac Newton's interpretation. So he would have looked at this, not just him, but someone of his era who is educated, would look up at the sky and say, ah, I know what's going on. In fact, the Earth is moving and spinning. It's the Earth that's actually going around the sun. So that's an entirely new perspective on what this is revealing. The Earth is going around the sun. And the stars themselves are distant suns. But again, Newton really didn't know what to make of this, the Milky Way. The crazy thing is even to Newton, this was a deception. Okay? But back up a little bit more. You know, your eye is drawn to Jupiter, right? But these distant stars outweigh Jupiter like a watermelon does a lime. They're much, much bigger than Jupiter. It's just a trick of perspective. Jupiter is just close to the sun, and the light is reflecting off of Jupiter, and that's why it looks bright, because it's fairly close. It's just a testament to how far away those stars are, that you can confuse them with planets sometimes in the sky, right? Sometimes you look at the sky and you're like, is that a planet or just a bright star? The fact that you can confuse that so easily is a testament to how far away those stars are. The crazy thing is, the Milky Way is so much larger than even the distances to the stars that it's incredible. Okay, we now know, like I said before, that all of the stars you can see by eye are embedded in this disk of stars called the Milky Way. In fact, the Milky Way galaxy is so big that if you shrunk it down to the size of the Pacific Ocean, the size of the entire solar system, that is, the sun and all the planets, all the way out to Pluto if you want, are as big as a maple leaf. So a maple leaf floating on the Pacific Ocean is the size of our solar system. Now imagine a bee on that leaf. A piece of pollen on the leg of that bee is the size of the sun on that scale. The Earth is like the size of a bacterium on that scale. And the nearest star to us is a half a mile away. So that's something that Newton didn't know. And in fact, when Newton thought of the universe, when Isaac Newton had a picture of the universe, this was Newton's picture. It was basically a bunch of stars. And these stars, again, are suns. It's like an endless sea of suns. And I think a lot of us actually have this picture now in our heads. If someone says, think of the universe, what is it? And you just close your eyes and you're just forced to think about it. A lot of people just say, oh, well, it's just this endless sea, you know, suns of stars. And it's just kind of like, it's kind of depressing. I don't want to think about it anymore. Okay? But it turns out that that's actually not at all what the universe is like. That's kind of what it's like on in a very small neighborhood around the sun. But that's not really what it's like on the largest scale. So this is wrong. Okay? We now know that the universe is not a universe of stars. It's in fact a universe of galaxies. And those galaxies are strung out across the universe almost like veins. It's almost biological the way they're strung out. It's filamentary. So these networks of galaxies run together. And so our universe is a big network of galaxies, and in each galaxy there are lots and lots of stars, billions of stars. And like I said before, our galaxy is the Milky Way. And what we would like to do is know how that came about. And so this course is about questions like that, how we came about understanding this. Here's some other things that Isaac Newton didn't know, that we know. Of course, the subtext here is we know a lot of stuff that Newton didn't know, not because we're smarter than Newton. Okay? Most of us are not smarter than Newton. I know I'm not. But we've had a lot more time to think about it. And more importantly, we have much more sophisticated instruments to study the universe than Newton did. And that's what's revealed what we know. So the overview of scientific cosmology today is that time and space and time, all began about 14 billion years ago in an event that's known as the Big Bang. And the universe has been expanding and cooling since that time. Because the universe was smaller then, right? So the universe is big today, and it was smaller then. It was very hot in the beginning. In fact, it was so hot that anything complicated couldn't exist. Okay, so imagine you're in this room and we started cranking up the heat. It starts getting so hot, everyone leaves. Okay, let's not get gruesome, but we keep turning the heat up. Eventually, it gets so hot that everything begins to melt. So these seats can't exist anymore, right? It's too hot. All the stuff that the seats are made of are just melted away. And then this liquid goo that is left, we keep cranking up the heat, and then that evaporates into some complicated gas. And then you keep cranking the heat up, and even the molecules that make up that complicated gas can't hang together anymore. It's so hot, the molecules are moving around so fast, they slam together, they break apart in their constituent atoms. You keep cranking up the heat. Now it becomes so hot that the atoms run into each other and knock the electrons off. And you have this sea of basically nuclei and electrons, and it becomes that's called a plasma. Then you keep cranking the heat up even more. And now the neutrons and the protons that make up the nuclei of atoms cannot hang together anymore. It gets so hot. And they must break apart. And now all you're left with is a sea of neutrons and protons and electrons. And you see, once you crank the heat up enough, the situation becomes very simple. And it doesn't matter what this room was made of before. Now that you've made it hot enough, it's just made of neutrons, protons, and electrons. Now you can envision continuing going up and up in the temperature scale, and then the neutrons and the protons break apart into quarks, into smaller whatever is down the line. But that's what we envisioned was going on in the early universe. It was so hot that it was really literally a sea of elementary particles. So more than primordial Earth, this is the primordial soup for real, right? This is the ingredients that eventually go into making everything. But the most basic ingredients were there in the beginning. And then from that, as the universe expands, it cools. As it cools down, gravity is also dragging things together. And as things drag together, they make more complicated structures like galaxies. Within these galaxies, stars form. And around these stars, planets orbit. And on planets that are the appropriate distance from their star and are made up of the appropriate stuff, you can have liquid water. You can have carbon and oxygen. And in principle, you could always have life. We know that happened at least once. So that's kind of the big picture story. You don't have to memorize the details of this, by the way, right now. I'm going to come back to all this stuff during the course. Now, the other thing that we've learned about this universe is not only does it have this kind of interesting timeline, but it's made up of stuff that's very odd. Only 5% of the universe is made up of what we would call normal matter. And what I mean by normal matter is anything on the periodic table, anything made of neutrons and protons. The other 95% of the universe is made of, as far as we can tell, very exotic material that we don't fully understand. And I'll talk to you about how we know it's there even though we don't understand what it is. That'll be a subject of one of the lectures, or a couple of the lectures. 25% of the universe is in the form of something we call dark matter. And something like 70% of the universe is even weirder stuff that we call dark energy. Dark energy is the stuff that propels the universe to expand at an accelerated rate. And dark matter is the stuff that holds galaxies together and tells them where to form and go. It turns out, as far as we understand right now, if there was no dark matter, there would be no galaxies like we see them today. So, I haven't told you why we know any of this stuff. I'm just sort of painting a picture. Does anyone have any questions about any of this? Anything spring to mind? Like, this seems totally normal? Okay, just shout them out, yeah.
Well, you said the universe must have been really hot in the beginning. Where did all of that energy come from to make everything that extraordinary temperature?
That's a very deep question. The question is, where did all of the energy come from that powered the Big Bang, basically, and that made everything? We do not know the answer to that question. That can be your final paper, to answering that question. We'll write it up and put my name on it. And yeah.
So you're saying since it was hotter before, all the planets and everything in the universe was closer together?
Well, yes. Everything in the universe was closer together. Most things in the universe were closer together in the past.
In their same form?
Well, no. So what you imagine is the original form is, you think of it as almost like perfectly smooth sea of neutrons and protons, basically. Something like that. Let's make it slightly more simple. A pretty uniform sea of hydrogen. But it wasn't perfectly smooth. There were little parts of the universe that have a little bit more stuff than others. And as the universe expands and cools, the other thing that's happening is areas that have a little bit more stuff expand a little more slowly than areas that have a little less stuff. And at some point, those areas that are expanding slow enough actually stop expanding and recollapse. And that recollapse is the seed of forming stuff. So it starts off smooth, little tiny ripples grow because of gravity, and they get amplified and amplified, and that's the stuff that gets made. So what starts off as almost a perfectly smooth early universe becomes this massively complicated, structured universe we see today. Yeah?
So as for now, there's no scientific explanation to how all the energy got together and started heating up.
Right. So it becomes a very, so the question is, you said, so there's no scientific explanation for how all this stuff came together in the first place and made the Big Bang. That's basically correct, and the reason why that's correct is that in order to know, it's impossible for us to observe, as far as we know, what happened before the Big Bang. So if we want to understand conditions before the Big Bang, it becomes very, very theoretical. Okay? What we know is that when we hypothesize that the universe was governed by the laws of general relativity, we can extrapolate the universe back to a point, and we predict that it should have been very, very hot. And all of the predictions we make based on the idea that there's a hot early universe are borne out by observations. Okay? But the question of why it was set up that way, that's almost beyond the realm. You could argue that that's beyond the realm of science. Okay? You could ask other questions like, why is there gravity? Okay, we know that there is gravity. I'll talk about that in this class. We know the Earth pulls down on us. Okay? There is a force, and we know what that force law is mathematically. We can write it down. But we don't know why, as of now. We don't know why it exists as it does. Why is the force of gravity there? Why do we have a force of gravity? Why are there electrons at all? Why are there protons? So there's some kind of basic ingredients that the universe just gave us. And what we're trying to do is try to figure out what are the fewest number of initial ingredients that we need to understand what's happening, what we see all around us today. Yeah?
You said dark matter is the energy that accelerates, creates, and guides galaxies?
So dark matter is the stuff that tells galaxies where to form and binds them together, as far as we understand. Okay. But again, this is not the first time, or this is not the last time I'm going to talk about this stuff. So We'll spend time on this. At this point, I'm just trying to kind of wow you, okay? I'm just trying to be like, isn't this crazy? I'm just throwing out crazy stuff to sort of get your attention. I'm not getting everyone's attention, but that's okay. I'm doing my best. So here's some other wow thing I'm going to try to do here. Sense of time. Okay? Now, it used to be, you used to be able to say a word like, you used to be able to say 14 billion years, and people would be like, wow, 14 billion years. That sounds like a lot. But now, when the national debt is like $50 trillion, a billion just doesn't seem like that big of a number anymore. But when you think about it in terms of time, it actually is a really big number. Okay? So here I've sort of made this cartoon timeline of the history of the universe. And I've put some events on this timeline, right? So the Big Bang happened, we believe, about 14 billion years ago. The current best number is more like 13.7, so about 14 billion years ago. The Earth itself formed about 5 billion years ago. The Earth and the Sun about that time. Okay? So that's not even halfway back. So the Earth itself, you think of the Earth as this old thing. But the Earth itself is not even half. You know, the universe is more than twice as old as the Earth. Almost 3 times. But even the Earth is quite old. Like, people don't normally think of how old the Earth is compared to sort of timescales we're used to thinking about. All right? So let's think about the dinosaurs, right? You think of the dinosaurs as sort of really long time ago stuff. But you're talking like 100 million years, maybe 150 million years. There's probably experts in the room that are going to correct my numbers. But you know, it's very, very recent compared to these stages. But if you think about it on a human scale, the dinosaurs were really long ago. I mean, all of sort of what you think of as Homo, sort of proto-human species, that was in the last sort of, let's say, give or take 2 million years. And all of recorded human history is just a tiny, tiny slice of this bar. So this is just nothing compared to the age of the universe. In fact, it's good to do this in kind of an analogy. So the universe is roughly 14 billion years old. Okay? So that's a 1.4 times 10 to the 10 years. Okay? A billion is 9 zeros, so it's 14 followed by 9 zeros. So if you write that in scientific notation, that's 1.4 times 10 to the 10 years. Are we good with that? Okay? So if the full expanse of time, if that 14 billion years was scrunched down into a single year, on that time scale, all of recorded human history would have occurred in the last 13 seconds over the course of a year. And William Shakespeare was writing his plays 1 second ago. So the universe is old. That's what I'm trying to say. So what I want to do now is just use this as a launching point to talk about doing the kind of math problems that we're going to need to do in this course. And it's basically figuring this thing out about Shakespeare writing his plays 1 second ago. How do you do that? Well, in order to work with a number like 14 billion, like I've said before, it's useful to use scientific notation. You don't want to write down all these zeros, and so we write things this way. If anyone has an issue with scientific notation, you can talk to me or Oliver, the TA, at some point, and we can go through those things. I know all of you knew how to do this at some point in your life, but some of you are sort of haven't done anything like this in 4 years, so I understand that. Now, in order to do this calculation, we're also going to need to understand what the difference between a second and a year is. The relevant ratio is. And it turns out that 1 year is about 31 million seconds. Okay, and you can figure out how to do that. There's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. You multiply all those numbers together, and you get 3.1 times 10 to the 7 seconds in a year. In a year, and the age of the universe is 1.4 times 10 to the 10 years. So how is it that I can so confidently say that if Shakespeare wrote, if the age of the universe was a year, then Shakespeare was writing his plays 1 second ago? How do I do that? So let me just walk through this. So actually, how do I do this? Someone tell me how to do it.
Proportions.
Proportions, yes. So ratios. So this is a ratio problem. Okay. So I've given the universe is 1.4 times 10 to the 10 years. Shakespeare lived in 1571. Everybody knew that, which is 442 years ago. So the question I'm asking is, 442 years is to 1.4 times 10 to the 10 years as x is to 1 year. Is that clear? So that you can write that as a couple of fractions. Is that okay? Are we okay? You sure? Right. So that's how I write this problem. 442 years divided by 1.4 times 10 to the 10 years is equal to x over 1 year. So how do I solve this? I multiply both sides by 1 year. And I find x is now I've converted 442 into scientific notation because it makes it easier. Divided by 1.4 times 10 to the 10. And the units remaining are still years. Now you can look at this right away and see that the number ought to be something like 10 to the minus 8. Because I have a 2 up top and a 10 down here, and I subtract the exponents to get this exponent. And then 4.4 divided by 1.4 is about 3. So I've just found that x in this ratio is 3.1 times 10 to the minus 8 years. That's not very useful, right? Because if I said, if you shrunk down the age of the universe down to 1 year, then Shakespeare was living 3 times 10 to the minus 8 years ago. You wouldn't know what to make of that. So you want to convert that into seconds. Remember, we already talked about how a year is about 3.1 times 10 to the 7 seconds. So you can already tell these numbers are going to come out of order 1. So if you work it out, you find that x is about 9 times 10 to the minus 1 second, which is about 1 second. So that's how we're able to say 442 years is to 14 billion years is the same as 1 second is to a year. Is that all right? Now, for a good fraction of this class, okay, those of you who are sort of economics majors or math majors or whatever, you're sort of annoyed with me, okay? But there's also a good fraction of this class that spends a lot more time reading than you do, probably knows a lot more history than you do, who maybe needed a little primer here, and so that's why I went through this, okay? And so I'm very aware of the fact that there's sort of wide range of expertise in this class, and talking to the people who are needing a little more help than others, please approach me with those questions. That's why we have a TA. That's why Oliver is our TA. He's a physics graduate student. He's really, really good at math, and he can help you with all of these things too. Okay? Any questions about that before I move on? Okay. So another thing we have to think about in this course that you don't have to think about in everyday life is the fact that the speed of light is not instantaneously fast. It's not infinitely fast. Okay? So light travels at 186,000 miles in a second. So it's not instantaneously fast. It's got a limit. Which means if this room were 186,000 miles long and someone in the back turned on a flashlight, it would take 1 second for me to know it, to see the light from the flashlight. Light is so fast that it can travel around the Earth 10 times in a second. But when you're dealing with things in astronomy, the distances are much larger than the distance around the Earth. So those delays start to matter more and more. So light takes roughly 8 minutes to travel to us from the sun. The implication of that is we are seeing the sun as it was 8 minutes ago. We're not seeing it as it is now. Okay? And in fact, it takes light 8 years to reach us from the nearest bright star. So we're seeing those stars in the sky as they were 8 minutes ago, at least for the nearest ones. So if you were to suddenly turn off all the stars, it would take 8 minutes for the first bright one to go dark. And then the more distant ones would start going dark later and later and later. Okay? But again, those distances to those stars I've mentioned before is nothing compared to the distance to other astronomical objects. So the nearest big so the galaxy of the Milky Way, it takes light 100,000 years to cross our disk, the disk of the Milky Way. Okay? So even traveling at that 186,000 miles in a second, it takes 100,000 years for it to cross the disk. But even the Milky Way is tiny compared with scales in the universe. So the nearest other galaxy to us, remember the Milky Way is a disk. It's got a twin sister over here that we call Andromeda. And the scale is about like this, actually. This thing is 2.5 million light years away. What I mean is it takes light 2.5 million years to get to us from Andromeda. We are seeing Andromeda. This picture right here is what Andromeda looked like 2.5 million years ago. It's what it looked like before there were people on Earth to look back up. So what this does, the neat thing about this is, if we look at things that are farther away, it allows us to basically look back in time. So the most distant galaxies that have ever been photographed are much, much, much farther away than 2.5 million light years. So the light that left this galaxy right here left it about 12 billion years ago, when a universe was a fraction of its current age. This is a galaxy forming in the early universe. And you see it's kind of messed up looking. When we look at galaxies that are really far away and therefore very young, way back in the beginning of the universe, they look a lot more messed up than galaxies do that are nearby us. And the way we interpret that is they're not done forming yet. Okay? They're sort of like teenagers going crazy. But the thing is, we can use this trick, this fact that light travels at a finite speed and therefore allows us to look back in time, for us to basically make a movie of the universe. We can begin to sort of slice together what the universe looked like at early times and later times and later times to build up a coherent movie of what the universe looks like over time. This image right here is the deepest image ever taken by humankind. It was just released a few days ago, about a month ago. It was taken with the Hubble Space Telescope. What this is a patch of sky that looks completely dark. So if you looked at it with the naked eye, it looks like there's nothing there at all. And it's a spot on the sky that's smaller than the tip of a laser pointer would be. And Hubble pointed at this one spot in the sky for more than 20 days. So that is, it's like opening your shutter on your camera and taking in light. And you know when you have a slow shutter, you can see darker things. You open that shutter for 20 days. But I'm not talking about a camera lens on a normal camera. I'm talking about the Hubble Space Telescope, which has 2.5 meter diameter lens for 20 days, orbiting above the atmosphere. So there's no clouds or atmospheric things to block what's going on. And this is the image that results. So many of the galaxies, and many of the galaxies in this picture, existed before the Earth existed. We're seeing them as they were before the Earth existed. In fact, the most distant galaxy ever detected is in this image. It's this red thing right here. It's very hard, very hard to see. It's very dim. It's just barely detected. But the galaxy in that spot appears as it was something like 380 million years after the Big Bang. Okay, so 13.3 billion years ago. This galaxy not only existed before the Earth existed, it existed before most of the atoms, many of the atoms in your body existed. So before the iron that's in your blood, before the oxygen you breathe existed, these galaxies existed. And in fact, what made the iron in your blood and what made the oxygen you're breathing is stars. Massive stars that exploded make atoms, heavy atoms, those atoms that are essential for life. So there's the famous line that we are all star stuff, but it's true, right? We are. If there were no previous generations of galaxies and stars, there'd be no building blocks for us. So in that sense, we are quite connected to all of this. So this concept of looking back in time in these immense distances, it's useful to come up with a unit to measure distances that are so large. And a very natural unit to use is something called a light year. Okay? A light year is a measure of distance, not a measure of time. Okay, so a lot of times, like on TV or something, people will say something, well, that was light years ago, like in some kind of, space show. It doesn't make any sense. Because a light year is that's like saying, that was 10 meters ago. It doesn't make any sense. So a light year is something like 9 times 10 to the 12 kilometers. It's about 10 trillion kilometers. That's the distance that light travels in 1 year. That's how it's defined. So you just take the speed of light, multiply by a year, and this is what you get. Now, of course, it wouldn't make any sense for us to quote everyday distances in light years, right? You don't say, I'm whatever, 10 to the minus 12 light years tall. Or the distance between here and there in light years, it just doesn't make any sense. But in astronomy, this unit of measure does make sense, and that's why people use it. Okay? So the nearest bright star is 8 light years away. The Andromeda galaxy is 2.5 million light years away. So light year is the distance that we want to use to measure distances to things. Does that make sense? Okay. So now that I've introduced a unit of measure, I'm going to end with talking about a sense of scale in the universe. Okay. But before I do that, are there any questions about anything I've talked about? Yeah.
Is there anything that travels faster than the speed of light?
So the question is there anything that travels faster than the speed of light? We're not aware of anything that travels faster than the speed of light. According to special relativity, so Einstein's special relativity, nothing that's traveling slower than the speed of light can accelerate to the point where it's actually traveling at or faster than the speed of light. As far as we know, that's a physical impossibility, and there's no evidence that anything does that. If something could do that, it would sort of rack the foundations of modern physics. It's very, very highly unlikely that anything like that can happen. Theoretically, it's possible that there are things that travel faster than the speed of light, but if you're traveling faster than the speed of light, you can never slow down and go slower than the speed of light. Those things are called tachyons. But that's a theoretical construct, and there's no evidence that there's anything like that exists. And then there are other things that travel at the speed of light, like light, or anything that doesn't have a mass, it turns out. So a photon is the particle that makes up light. Photons travel at the speed of light. Any particle that is massless, any other type of particle that is massless would travel at the speed of light. Anything else? Yeah.
Will we ever be able to explore the galaxy? Because even if we could travel at the speed of light, that would work.
That's right. That's a good point. So that's a point that I'll come to in a couple of lectures. But the question is, will we ever actually be able to explore the galaxy? it's highly unlikely. I mean, maybe in a long time, if we really figure out how to travel fast, we can do it. So, you know, to travel across the galaxy, I said, even at the speed of light, takes 100,000 years. And getting a spaceship going a fraction of the speed of light takes an incredible amount of energy. So you would need a brand new, entirely different source of energy, some kind of fusion energy. The idea would be even traveling at those speeds, you would need to sort of plan on very long distance travel. So you probably would have to have colonies on your ships, very big ships with lots of people and generations of people as you traveled across the galaxy. In principle, you could get to the nearest star and back in a human lifetime, because there's also time dilation helps you a little bit, so you don't feel as old when you get there. Everyone, when you come back, will seem very old, though. So there's things like that. So it's going to be a long time, okay? But the subtext of that is all the stuff I'm teaching you about here, we've never been there, right? Even the nearest star, we've never been there. We're not going to go there for a very, very long time, right? We'd like to go to Mars. We'd really like to go to Mars. Mars is so close, so close. The moon is nothing, right? We've been to the moon. We're all proud. It's nothing, right? So, you know, so getting to the next star is a huge deal, would be a huge, huge deal. And that's a long time from now, probably. So the way you got to learn about these things is you got to be much smarter than that. You got to collect the light that the stuff is emitting and squeeze information out of that light to teach you about things. But it's amazing what you can learn by just doing that. And that's why we build really, really big telescopes. Okay. So let's back up. So I've done a sense of time. Now I'm going to do a sense of scale. This is a classic thing called powers of 10, which I love. I mean, I think I was like in grade school or something the first time I saw this. And I'm like, that's probably why I became a scientist. It's just like, whoa. So I'm going to show it to you people. Hopefully it's not too quaint for you. There's movies that do this too. And in fact, I've linked one to the blog that's better. But there's something about this that I really like. So what is this? So we're looking at the eye of a bee. Okay, a bee, pretty small thing. And we're looking at the eye of that bee. That's like the smallest thing that you're going to deal with in a day-to-day existence, right? There it is. This is 1 millimeter across. 1 millimeter across. And what I'm going to do now is I'm going to zoom out by a factor of 10. And there's going to be a little red box in the middle, and it's going to be that 1 millimeter. So if I zoom out by a factor of 10, there's that bee's eye we were just looking at, and there's the bee. Okay? Factor of 10. Let's zoom out by another factor of 10. Now we see the bee is sitting on a flower. In fact, it's a lily. Okay? 10 centimeters, bee. Now it's 10 centimeters. We started at 1 millimeter, 10 centimeters. Let's do another one. Now this is a meter. Okay? Now we see that this lily is on a lily pad, and the bee is on that little flower. And it's part of a pond. So we see part of a pond. Now we're going to go out another factor of 10 from the pond. Now we're at 10 meters, okay? Starting to be the size of a room or whatever. This is the size of this pond at 10 meters. That's a pretty big scale, 10 meters now, okay? And it wasn't that many powers of 10 from the eye. 1, 2, 3, 4. So this is what an exponent is. 4 powers of 10. Let's go out another factor of 10. There we are. This is roughly the size of a football field or a baseball field. Okay? And in fact, this is the San Francisco Center for Arts and Sciences in Golden Gate Park. So it's a picture of Golden Gate Park. A good chunk of the park on the scale of 10 meters. Let's go another factor of 10, a kilometer. Now we see a good chunk of all of Golden Gate Park, which is a big park. So now we're on the scale of like a big area in the city. Let's do another factor of 10. Now we see a good chunk of San Francisco. Just orienting you. Another factor of 10. There's the whole Bay Area. 7 million people live in this box. Let's do another factor of 10. That's California. Okay? The whole state. California is big. There we are. Let's do another factor of 10. North America. 10,000 kilometers. That's about as big as you're going to deal with in your day-to-day existence, right? You might take a plane flight. Okay? That's kind of the limit of what we're going to be doing. But let's keep going and see what's there. There's the Earth. Another factor of 10. Now, the moon is just outside this box. There's no moon there. Okay? Most people think the moon is like here. No, it's way off here. There's nothing there. There's actually a lot of satellites orbiting around, but it's really not that much there. Let's go out another factor of 10. There we see the moon. That's the orbit of the moon. It's pretty far away. So I was making fun of how close the moon was. It's not that close. Now the reason why it looks like the moon is going around in a big ellipse, it's actually going around in something much closer to a circle. But this is the orbit of the moon seen edge on, right? So if you see a circle that's like this and I tilt it, it looks kind of like an oval, and that's what that is, okay? Factor of 10, 10 to the 6 kilometers, 10 to the 9 meters, that's the scale of the Earth-Moon system. Another factor of 10. No other planets on this view, okay? But here's the path of the Earth going around the sun. Here's the moon going around the Earth, okay? The crazy thing is, on this scale, this is a huge, huge distance, right? Remember how many powers of 10 since the size of the Earth? The Earth tracks this distance in 4 days. That's fast. The Earth is going really fast around the sun. The Earth moves at about 2.5 million kilometers a day. Let's go out by another factor of 10. There's the Earth, and there we're finally seeing Mars and Venus, the orbits of Mars and Venus in there. But sometimes Venus is on the other side of the sun, whatnot. But that's where the orbit tracks are. That's kind of the distances to the planets. And you can see, getting to Mars is a lot farther than getting to the moon. A lot farther. Let's go another factor of 10. There we go. So finally we see the sun. That's where the sun is. And there's the orbit of Jupiter. This is the Earth. 10 to the 12 meters. But that's not the whole solar system. Another factor of 10. There we go. 10 to the 13 meters. It takes light 8 hours to cross this. Now, if you recall, the Earth is about 10 to the 7 meters in size. So you can compare this to 10 to the 13 meters. That's the size scale we are there. That's 1,000,000 times. So the size of the solar system is 1,000,000 times the size of the Earth. And if you take it down, 1,000,000 times smaller than this is just 10 meters. So it's like the Earth to the solar system is the same as basically this room to the Earth. Let's go out another factor of 10. Okay. At a distance like this, you could only see the sun from a spaceship. It would just be this bright star. And it would be very difficult to see the reflected light from Jupiter, much less the reflected light from Earth. Now around this point, there's the Kuiper Belt. And there's objects that are kind of like Pluto, which is now declassified from as a planet, like rocks and stuff orbiting around out there. Another factor of 10. There's just this thing that we call the Oort cloud out there, but really there's no other stars. There's still, the orbit of Pluto is like this. There's just other rocks and stuff out there. No stars within this picture. Let's go another factor of 10. Nothing. Right? There's no other stars here. Another factor of 10, right? You are here, very lonely. Another factor of 10, we're now beginning to see the nearest stars, okay? So Proxima Centauri is a close by star, 3 or 4 light years away. But the brightest stars we see in the sky, in fact, are not in this picture. The brightest stars in the sky are just so bright that they appear brighter than these things, even though they're farther away. Now 10 to the 18, now we're starting to see lots of stars, okay? Beginning to see background stars. These are all the stars within about 100 light years. Let's back out again. This is 1,000 light years, 10 to the 19 meters. We're seeing a chunk of the galaxy. And these bright points here are sort of newly born stars, nebula of gas that we're starting to see. Add another factor. Now what I've done now is I've skipped 2 factors of 10 because it was getting boring. Factor of 100. There we see the galaxy. Now of course this is not a picture of the galaxy. Why is that? How do I know for sure this is not a picture of our galaxy? A real picture? Yeah, you could never get there. This is 100,000 light years across. Okay? So imagine you'd have to send a spaceship up there, take the picture, and then bring it back down. Okay, that's not enough time for that. Yeah?
What's that? It's like a bright in the middle.
Yeah, that we believe that the Milky Way has a big bright spot in the middle. So the middle of our galaxy, and lots of galaxies, is brighter than the outer parts. That's called the bulge. So there's a bulgy part in the middle. There's a very dense, there are many more stars bunched together in the middle of the galaxy than there are in the outside of the galaxy. Okay, the sun would be about here in this picture. So we live kind of in the outer part of a spiral arm of our galaxy, sort of out of the way. We're not in the middle where all the action is, but we're out here somewhere. Let's go another factor of 10. Wait, did I do 100? No, another factor of 100. No, I'm jumping by hundreds. If we jump by another factor of 100, there we see this nearby galaxy called Andromeda. So that's our partner, our sister. It's about our size. And the other thing you see is both Andromeda and the Milky Way, both of these 2 big disk galaxies in the neighborhood, have little galaxies orbiting around them. They're little satellite galaxies, little dwarf galaxies, that orbit around the big galaxies much like planets orbit around stars. So we have our own little neighborhood of little galaxies that swarm around us, and Andromeda has its neighborhood of little galaxies that swarm around it. I'll talk about this later, but Andromeda and the Milky Way are headed towards each other, and they're going to crash together in a few billion years. Yeah?
If we've never been outside our galaxy, how do we know this?
Thank you. The question is, if we've never been outside our galaxy, how the heck do we know this? How can you make this picture? Well, that's kind of the hard part. That's one of the hard parts, okay? So what you do is you look up at the sky and you take measure of things, okay? And it turns out that in the sky at night, you can in fact see with your naked eye a little blurb of stuff that just looks like a smudge, and that's Andromeda. That's the Andromeda galaxy, okay? And we know it's there, and in fact we've known the Andromeda nebula has been in the sky way before people knew even the existence of galaxies. And what people have done is they've studied Andromeda with big telescopes and tried to figure out what's going on with this smudge in the sky. And eventually people were able to resolve individual stars in it. There's tricks that we use to figure out distances to things in astronomy, and that's really the hard part. One of the really hard parts of astronomy is figuring out the distances to things. And so what you do is you figure out the distance to the object, you look at it and study it and study it and study it, and eventually realize, hey, that's a galaxy. It's outside of our own nest of stars. And you figure out that it's 2.5 million light years away. And in this course, I will talk about how we figure out distances to things. But it's not easy. It's not an easy task. And it's actually an amazing thing if you think about it, right? We're floating on this leaf in this galactic ocean. We live on a microscopic planet, but yet we've figured out what's going on these scales. It's amazing. Yeah?
Do we know if we're orbiting around any other galaxy? Like, is Milky Way orbiting?
We don't think so. We think they're basically coming at each other. So the Milky Way is part of a larger flow of galaxies. So it's sort of both Milky Way and Andromeda are streaming in one direction, it seems like. But generally speaking, we're basically like the two biggest kids on the block nearby, and we're about to run into each other. So if I zoom out by another factor of 10, this is now, well, this is the same scale. It's 1,000,000 light years. This is the Milky Way and Andromeda. Every single dot on this picture is a galaxy with 1,000,000 to 100,000,000 to 1,000,000,000 to 100,000,000,000 stars. Let's go out another factor of 10. All of that local group, the Milky Way and Andromeda, are here. And here are all the other galaxies around us. Every dot on this picture is a galaxy. This big thing over here is called the Virgo cluster. It's a big cluster of galaxies that's in our, this is actually still our neighborhood. And if anything, we're kind of going this way. Let's go out another factor of 10. Again, the universe is littered with these galaxies, but you begin to see a structure in them. That they're strung out, they like to live together, and as you zoom out enough, you begin to see that galaxies prefer to live on filaments. They're strung out along these large-scale structures, and they tend to stream along those structures and collide together. Where these highways of galaxies run together, that's where we see things called clusters of galaxies and superclusters of galaxies, like here and here. This is an immense size scale. This is 100,000,000 light years. Just that little bar is 100,000,000 light years. We have actually mapped the universe out to distances larger than this. This is one of the largest maps that's ever been made. It's about 1,000,000,000 light years across. It's a real map. And each point is a galaxy. Now the reason why it's fanned out like that, because when you do a survey with a telescope, you have to figure out where you're going to look in the sky. And at a certain point you hit the land is there and you can't see on the other side of the Earth. So there's some distance over which you can look, and that creates kind of like a fan-like shape. So you imagine you take the telescope and go like this, and then you go like this, and then you go like this, and you attempt to build a map. Almost like you're mowing the grass in the sky. And so that's kind of what this is. This point here would be us. As you go out this way, it's more distant galaxies. And of course, this keeps going, right? And you get to the point where you're at about 10 to the 10 light years. And this is what we call the visible universe. Now, this doesn't mean that this is the whole universe. What this means is this is the piece of the universe that we can see given the amount of time that the universe has existed. Does that make sense? If there was stuff out here, it would have taken more than 14 billion years for light from that stuff to reach us. So that defines basically a sphere, an horizon, beyond which we cannot see. So that's what we call the visible universe. And what we would, and that's one reason why when people ask the question, how big is the universe? Well, we don't know. We know it's bigger than this. And it could be infinitely big. It could be 100 times as big as this. So these are the kind of questions that people ask. Right. Are there any questions about that? Yes?
What about invisible universe?
Invisible universe?
Can't see.
Well, that's a good point. That's a good question. So there's stuff we can't see. Okay, there are lots of things that we can't see. Like, for example, radio waves. There's radio waves going all through this room right now, right? If your phone rings, you know that. We can't see them. There could be other stuff that we can't see, like neutrinos. There's things called neutrinos going through us right now that we can't see. And there could be other types of matter. In fact, dark matter, we believe, is another type of stuff that we can't see. That's why we call it dark, because it doesn't shine. Okay? So there could be all kinds of stuff in the universe that we can't probe by looking at the light. So to look for that, to look for the invisible part of the universe, we have to think harder and figure out implications for its existence. Okay? And that's one reason why we know about dark matter, because there are things going on that are unexplained by the visible matter we see. That's another reason why we think we know about dark energy, because things are happening in the universe that can only be explained by evoking this exotic stuff that we can't see. Now, a lot of people think if we start talking about things we can't see, then you're just making things up. You guys don't know what you're talking about. Okay, that's a common reaction when you start talking about these kind of elements. But again, there are a lot of things in this world that we're very familiar with that we cannot see. Okay. One example is the wind, right? The wind blows and knocks stuff down. You can't see it, but it's still doing things. So if you have an essence of something that's actually doing something, you have evidence that something is happening. And like I said before, radio waves are another great example. We can't see them. Our eyes can't detect radio waves. And in fact, our bodies can't really detect radio waves. We have to build special instruments to detect them. So in principle, there could be other kinds of phenomena in the universe that are not visible that I've just completely washed over in this entire picture. In fact, I have. Yeah. So that was a great question. Yeah?
Small tangent. Density for the galaxies in cluster like that, can that be factored into explaining how or why the particles condensed prior to the Big Bang? Is that
So the tendency, so the question is, the tendency for stuff to cluster together and form these kind of structures, can that in any way be used to try to understand why stuff all clustered together before the Big Bang to create the Big Bang itself? You know, you can try to build very complicated theories to try to say what about the universe that we can observe now can teach us about what was going on prior to the Big Bang. But it's very, very speculative, and the structures are really not the same. You know, like, so this is gravity in its simplest sense. And given what we know about the universe now, it is not going to stop expanding and like recollapse and create another Big Bang, at least in a very simplified sense. All I can say to you is there are theories that people are trying to build to explain the phenomenon of what happens in a Big Bang type scenario. But it's quite esoteric, and it's difficult to explain in the context of, you know, why stuff clumps together. And the reason why stuff clumps together in the universe is quite well understood. The reason why there's a Big Bang is a huge, huge open question. Okay, I think that's a good place to stop, and we will see you next time.